So thanks for the introduction. This is joint work with Ozan Solmas, Jan von Laten, and Roger Wattenhofer. Ozan is also in the audience here. And what we worked on is optimistic MEV in the Ethereum layer 2s and why this just might be the answer, why Blockspace is always in demand. So one of Ethereum's biggest challenges has been scaling. And in the past, sort of high demand on the layer 1 has led to congestion and expensive fees there. And now instead of just making the layer 1 bigger, Ethereum chose, at least in part, to go a roll-up-centric roadmap. And the idea here is that transaction execution moves to the layer 2s, and then the layer 2 rollups, they post their data on the layer 1 for security. And this sort of design already made transactions significantly cheaper on the layer 2s than on the layer 1. But then we also had the Denkun hard fork, which through EIP 4844 further lowered the cost of posting data on the layer 1 by the introduction of blobs. And this again made the transaction fees dramatically cheaper on layer 2s. Now, layer 2s, they're really no longer experimental. They are core to Ethereum. By early 2025, almost half of all decentralized exchange activity was happening on layer 2s, and assets worth over $40 billion are secured across rollups like Arbitrum, Base, and Optimism. Now, in this work, we wanted to look at MEV on these layer 2s, but what really distinguishes the layer 2s from the Ethereum layer 1 that makes us believe that there are some critical differences, which then also sort of change how MEV might behave differently on layer 2s in comparison to the Ethereum layer 1. And the first is obviously fees. On the Ethereum layer 1, gas fees are relatively high, and they're much lower on the layer 2s. Now, to block times on the layer 1s, we currently have 12-second block times. On Optimism and Base, at least when we were doing this analysis, it was 2-second block times, and on Arbitrum around 1/4 of a second. Then we also have transaction ordering on the layer 1, as we saw in an earlier talk as well, or at least hinted at. The builder auctions control inclusions. So blocks are generally built and optimized for value, so MEV, and this is done by specialized builders that compete with each other in what is referred to as a PBS auction. Now on the layer 2, sequencers handle ordering, either through first come first serve, as it's done on Arbitrum, or priority gas auctions, as it's done on the OP stack rollups. And then the last difference that I will highlight here is the mempool. On the layer 1, it is at least generally public, even though some transactions take a private path. And on the layer 2, the mempool is generally private. And this is the case for the 3 rollups that we are focusing on, which are Arbitrum, Base, and Optimism. Now, the important thing is that these differences in between layer 1s and layer 2s, they really also change how MEV bots operate. So before I discuss how these changes do that, I first want to take a quick step back and just quickly reintroduce MEV, which just refers to the value that can be extracted through including, excluding, and reordering transactions in a block. Examples of MEV include sandwich attacks, cyclic arbitrage, sex-dex arbitrage, and liquidations. And I think the most important thing here that I want to point at is that on the Ethereum layer 1, MEV usually involves off-chain computation. So you look off-chain, what could a profitable trade be? And then only then do you submit a transaction that executes this trade. And then those transactions are sent through an MEV auction, meaning that at least in most cases, they only will be included in the block if they execute as planned and make the profit. Now, on the layer 1, MEV, the MEV landscape is very well studied. We understand this phenomenon quite well, I would say. But what we really do not understand too good yet is how it is different on the layer 2. And what I want to do now is I want to look at how cyclic arbitrage, which will be the kind of MEV we focus on, looks on the layer 1, where we have this traditional MEV, as I will be calling it. So on the layer 1, we have the off-chain computation of profitability. As you can see in the example here on the slide, we have a bot that takes advantage of a cyclic arbitrage. It makes a profit by swapping wrapped ETH and another token and then going back, so it makes a profit in wrapped ETH. But what we can see, and what is the important thing I want to point at here, that if we look at the call data, which is shown on the top here, everything is specified. So the pools through which this transaction will go, it is specified in the call data, and the amounts that the transaction will swap, that is also specified in the call data. So this tells us that this opportunity was known to the bot before. I mean, it's literally writing it in the call data, and that it was only submitted after it knew that this opportunity should exist. How is this different on the layer 2? Let's look at a successful cyclic arbitrage on the layer 2. And at first, maybe it doesn't even look that different, because again, we see that here someone makes a profit in WebDev. Okay, they go through an extra pool in comparison to the other example. But other than that, it doesn't look too different. We only really see the difference if we look at the call data now. It's like minimal, it's non-informative, it's not telling us anything about sort of what this trade will be doing. And this sort of suggests that this opportunity, it wasn't known to this bot in advance. It found it by doing on-chain computation to find these price discrepancies and then take advantage of it. And that really highlights the difference between traditional MEV, which is prevalent in cyclic arbitrage on the layer 1, where we have off-chain computation and a very high success rate, and optimistic MEV, which we find to be prevalent on the layer 2s, where we have this optimistic submission of transactions, and along with that, also very high failure rates, as I will be showing in this talk. So a bit more formally, what we call optimistic MEV are strategies where the profitability is decided on-chain during execution, and that leads to speculative transactions that often end without any trade. And in our work, as we will focus on cyclic arbitrage, so arbitrage between DEXs on the same blockchain. And the reason that we decided to do that is that with cyclic arbitrage, the entire opportunity can be discovered and executed within one transaction on chain. Okay, so let's look at what we actually did now in our work studying this novel type of MEV that is very prevalent on the layer 2s. The first thing we, of course, needed to do is we needed to analyze data. And for that, we have a multi-stage pipeline. The first thing is we collected raw data from the Ethereum layer 1 to have a comparison, and then the 3 biggest layer 2s in terms of DEX volume, so Arbitrum, Base, and Optimism. Then we went ahead and found contracts on all of those 4 chains that engage in cyclic arbitrage, that we find to be doing cyclic arbitrage. And then the last step is that we classify transaction behavior. And we classify it in 3 dimensions. So the first dimension is transaction purpose. If the transaction comes from a bot that we know to be doing cyclic arbitrage, we label it as cyclic arbitrage and not otherwise. Then the second dimension is DEX involvement. There we differentiate between 3 categories. The first is trades. So these are transactions like you can see now in the example here, where the bot, it calls the DEX many times, it reads the state, but it will execute at least 1 trade on the DEX. And then we also have the second category, which is just interaction. It looks very much the same, except for that at the end, after reading the state many times, interacting with the DEX many times, it doesn't execute any swaps. And then the final category we have is residual. That's just the rest, where they don't even interact with the DEX. And then we also differentiate execution outcomes. So did the transaction execute or did it revert? Okay, so with that, we're essentially set up to look at how optimistic MEV looks like. And I want to start by showing you sort of the outcomes of the transactions that we associate with these cyclic arbitrage bots across the different chains. So each of the pie charts here, what it shows you is it shows you in red the actual trades, so where there was a trade that actually occurred. And then in orange, it shows you the interactions, where it interacts with the DEX, but doesn't do any trades. And in yellow, it shows you the reverts. Now, on Base and Optimism, we find that less than 12% of transactions actually result in a trade that come from these cyclic arbitrage bots, and more than 88% of them are speculative probes that don't swap anything. And a small fraction also revert completely. Now, if we compare that to the Ethereum layer 1, where more than 95% of these transactions succeed because, well, they're pre-computed off-chain and only submitted through the auction, and then generally only execute once they're guaranteed to be successful. So there's a huge difference here, and Arbitrum we find to be sitting right in the middle, where 50% of transactions succeed, while the other half fail to execute a trade. So even though for all these bots on the 4 chains, we all labeled them in the same way, we labeled them as wanting to do cyclic arbitrage, the way they go about it, we find to be radically different. On the layer 2s, they use optimistic MEV patterns and most transaction executes with no successful trade, while they use traditional MEV patterns on the layer 1, which generally leads a successful trade. Okay, then the next thing I want to show you is how big is this phenomenon. And I want to do that by looking at the gas usage of the various types of classified transactions, again on the 3 layer 2s and on the Ethereum layer 1. And for now, what I'm showing you on the slide is the gas usage of all transactions where the caller is not a cyclic arbitrage contract. And then let's add sort of the other categories one by one. So first, now in red, the only thing that I added is the gas usage from transactions that belong to the cyclic arbitrage trade category. So those that come from a cyclic arbitrage contract and actually execute a trade. So these transactions where we identified that they are coming from someone that performs cyclic arbitrage. And presumably, this is also the ones that result in a successful cyclic arbitrage. And here, when we look at this plot, we don't really see a very significant difference between the 4 chains. The relative gas usage of these types of transactions is really not radically different between these 4 chains. We only see the radical difference when we now add the cyclic arbitrage interaction category. We call that this is gas usage that comes from transactions whose caller is associated with cyclic arbitrage. They do interact with the DEX, so presumably to do on-chain computation, but they do not execute any trades. And this is really where we see a significant difference between the layer 2s, especially the 2 OP stack ones, and the layer 1. On the layer 2s, generally more than 50% of gas usage from cyclic arbitrage bots does not execute any trades, pointing towards their speculative nature, as we saw previously already. And in total, on optimism, cyclic arbitrage accounts for 55% of all gas used. On Base, it's 51%, and on Arbitrum, it's quite a bit lower at roughly 7%. But I think the most important thing to highlight here is that in the Q1 of 2025, more than half of the block space on the 2 OP stack rollups that we looked at, so Base and Optimism, was taken up by this optimistic MEV activity. So then, given that this is a very big thing that we observe to be happening, we also wanted to understand how these bots behave a bit. So the first thing we want to look at is, again, the speculative nature. And we do that by looking at the call data. So this is you can think of the call data a bit as information that is given to the contract that executes it then in order to then perform the cyclic arbitrage. And what we notice here is that on the 3 layer 2s, they generally reuse the call data many times. This hints at there not being too much up-to-date information in the call data. Because if you remember from the example there, we had the exact pools and the exact amounts there. You wouldn't expect that the exact same opportunity exists like 20 times in a row, and especially not 8 million times after each other, which we actually found one bot on Optimism reusing the same call data 8 million times. At the same time, we also have the call data length shown here, and that for many of these bots is already also very small, which again hints at there being minimal information conveyed through the call data, and that they're in fact searching on chain. Then what we also looked at is the competition. So the cumulative optimistic gas usage consumed by the top 10 bots, just to get a bit more of an idea of the landscape. And what we find there is that around a fourth of gas is used by the top 10 bots on Base. It's 42% on Arbitrum, and then even 70% on Optimism, which hints at a significant degree of centralization, but this is something you're quite used to when looking at MEV. And then finally, as we saw, optimistic cyclic arbitrage bots consume really the majority of gas on Base and Optimism. But what we also wanted to know, do they also pay the majority of fees? So to some extent, are they paying their fair share? And for that, we also looked at the fees that are being paid by bots on these two OP stack rollups. So this chart now shows the average gas price paid by cyclic arbitrage bots compared to all other transactions on Base and Optimism. And the orange here is for the cyclic arbitrage bots, and the blue bars is sort of for the rest. And what you can see is that the bots are paying 3.5 to 6 times less in fees than regular transactions on these OP stack rollups. And that despite paying the lowest fees in the system, what we also find is that they are actually the main beneficiaries of added block space. So these two OP stack rollups, they have raised their block limit several times, and we find that most of this capacity was filled up not by user activity, but by these low fee optimistic MEV transactions. So now we know that optimistic MEV is happening on these layer 2s. And the final thing we wanted to understand, or that I'm going to present here, is what is actually driving it. And for that, we performed a regression analysis, which found that 3 clear drivers of optimistic MEV activity, as well as successful optimistic MEV transactions. So the first here is Ethereum price volatility. What we find is that when prices move rapidly, arbitrage opportunities open more frequently. And on the L2s, the bots capture more opportunities and spam the network more with speculative transactions to catch these fleeting price gaps. The second driver is retail trading volume. Retail traders often submit less optimized swaps. This creates temporary price inefficiencies, which these bots then attempt to exploit. And the final one is a lower usage of DEX aggregator usage, where trades bypass aggregators and go direct to pool. And again, this leads to more price differences, which increases the number of arbitrage opportunities, and the bots are responding to this. Now, this brings me to the conclusion of this presentation, where I just want to quickly discuss sort of the impact that optimistic MEV is having on the ecosystem. So given its size, optimistic MEV certainly impacts the layer 2 ecosystem. I think there's not too much debate to be had about this, as it accounts for more than half of all gas usage on Base and Optimism. So the cheap block space that is being offered by this network, it is largely being consumed by these speculative probing transactions instead of user transactions. Now, this constant flood of low value transactions, it adds hardware requirements for node operators, which might over time lead to increasing centralization pressures, because there might be fewer remaining nodes that are well equipped enough to handle the load. And finally, optimistic MEV doesn't behave like normal MEV, so maybe our mitigation strategies don't work anymore, and so on. So there's a bit more work to be done in this area as well. So in summary, this optimistic MEV, we find it to be dominating gas usage on layer 2s, especially the OP stack one, and we think that it must be considered in future L2 design and MEV mitigation strategies. And yeah, there's a link to the paper, and I'm happy to answer any questions.
Thanks for the talk. So just one question. I'm just wondering if something similar is happening on Solana as well.
I believe so, even though we didn't look at it. But there are some sort of blog posts that hint at similar activity being happening at Solana, on Solana as well.
Okay, thank you.
Thank you. Do you have any idea why this happens much less on Arbitrum?
I think there's several reasons. One of them is that Arbitrum, so the minimum base fee, Arbitrum set it significantly higher than the other two. That means that while the other two can go down to one way, this isn't the case on Arbitrum. So on average, fees are higher on Arbitrum, but there were periods of time where fees were higher on Base and it was still happening more on Base. And then there's like several additional differences where we cannot pinpoint exactly what it's causing is, but one is that Arbitrum is first come, first serve ordering. The other two are priority gas. So with the other two, you can bid like a low gas fee. You know that you're at the end of the block. User trades happened before you that you can potentially take advantage of. That's one other difference. And then the other one is as well that the block times are different. They're 2 seconds on the 2OP stack one, and they're a quarter second on Arbitrum. So yeah, so we don't know exactly sort of what of these many differences is causing it. I would guess one of the main ones is the fee difference, but the other two need to be contributing. The others need to also be contributing to it.
Thanks.
One last question.
Thank you for the talk. So actually, it was certainly just back in the day when I was doing cyclic arbitrage on Solana. This was happening in 21, and in fact, most of the block space was taken up by all of this stuff. But it also was happening on Ethereum in 2020 and prior to Flashbots. Flashbots, of course, like enabled this to happen because now you get to actually bid for a specific spot on the block. But before, you would just submit blind transactions with slightly changed gas fees to make sure that you were kind of trying to be the last person that got in.
But
Right.
were you also like computing off chain?
Yes.
Ah,
So you compute off chain the way, and I think it's what's happening here. You compute off chain. Once you see an arbitrage opportunity, of course, you don't know the size of the arbitrage opportunity by the point that your transaction lands on chain. So you do like a binary search, or you do some like simple like grid search to figure out what the size of the trade should be. And then if it fails, whatever, you've paid the gas fee. But
I feel like on Arbitrum it might be similar to that, but based on Optimism, we feel like they're not even doing anything off chain.
they're just like
They're
constantly
literally just
spamming.
going completely blind on chain. But I think Ozan might have a comment to that.
In the table, some of the call data are low. And
what, sorry?
some of the bots uses very low call data.
Yeah.
And what they do is they continuously change like set of contracts that they are going to consider. Maybe like in the call data, they put like 10 different pool contracts, but it is not like those 10 contracts are like an arbitrage because sometimes they fail. But what they do is they check all those 10 contracts instead of like randomly checking the pool contract. So I guess maybe you can argue, depending on the time period, they adjust the contracts, but they still don't know if the opportunity is still there for them.
Yeah, the thing people would do is they would be like, cool, like it looks like there's some mispricing, which likely by the time that the transaction lands, will have other mispricing, if other people capture other arbitrage. Right, because like if you only arbitrage triangular pools, you could end up in other places that have arbitrage because you haven't actually done it over the whole graph. And so I think like that's when gas is really, really cheap, of course, you're just gonna do that because some people are gonna capture some triangles and you're gonna get some of the other ones.
Yeah.
But I think it's still, people do pre-compute like that there will be an arbitrage at some point, or there is an arbitrage currently, and then try to, because if you're just blindly spamming, I think you would just go block and the gas price would shoot up pretty quickly.
Yeah, I guess they're not doing it completely blindly. They are controlling to some extent that the base fee isn't going up, but it feels like they are just regularly going in and they're self-controlling for the base fee, like amongst each other, not going up.